Okay, so I think we can get started. So first of all, I would like to say that it's a great pleasure to welcome my colleague Shiwei Zhang here for a few days. And I should also say that this is actually a joint invitation together with Felix Werner and Tarek Yefsa. So it was very serendipitous that Shiwei could visit just exactly the same day that we had all this beautiful talk by Tarek. So Shiwei did his PhD at Cornell University in the mid-90s. And he always been an expert at computational physics. He moved as a postdoc, I think, to Ohio and Los Alamos, if I remember correctly, and then became a professor at Williams & Mary, where until recently he held the title of, I think, Chancellor Professor of Physics, is that correct? Where he stayed until we had the good fortune to actually be able to attract him full-time to the Flatiron Institute at CCQ. And it's really a pleasure to welcome Shiwei. He's has done many contributions to the field, but he's in particular very well known for having introduced this constraint path, auxiliary field quantum Monte Carlo method that alleviates the minus sign problem in these simulations with auxiliary field. And recently he's done many beautiful contributions, in particular to cold atoms. So the floor is yours, Shiwei, and thanks for accepting the invitation.
Thank you so much, Antoine. Felix and Michelle, for the hospitality. It's a pleasure to be here. And thank you for staying through the marathon session today. So I am going to, I have this agenda to talk, hopefully to echo this wasn't planned, but seems like it's resonating very, very well, hopefully to echo what Antoine was telling you about computation, and he was also telling you a lot about the experiment, and what you heard from Tarek about the tremendous, exciting progress. But hope to echo this and show you how the advances in computation, and I will illustrate the sort of field, how through benchmarking collaboration, which are key factors in the progress, but also through method development. And for this, I'm going to focus on the field of quantum Monte as I mentioned, to give you a thinking about the sign problem. Thank you.
That means you have to repeat everything you just said.
I think the people in the room heard me. Apologies for, well, what I said before was in French, but now it's going to be in English. So, going to tell you about how to think, introduction on quantum Monte Carlo and how to think about the sign problem and the progress in terms of controlling it. And then two applications to echo this synergy. One in 2D Fermi gas, as you heard beautifully from Tarek. And then the other one on the Fermi Hubbard model. Experimentally, that would be with an optical lattice. And in particular, talking about the connection with Cooper rate superconductivity. And if there's time, maybe FFLO order. I don't have to finish this agenda. Interrupt me. Hopefully, it's useful for you. So the Hubbard model, you've already seen this. We have a simple Hamiltonian with electrons hopping on a lattice, two kinds, spin up and spin down, and on-site interaction. And this is sometimes called the Ising model of quantum many-body physics. But of course, the key difference is that with the Ising model, eventually we were able to at least numerically solve it very cleanly. And here, we are not there yet. This model can also be used to model the Fermi gas that Tarek was discussing. The same Hamiltonian written here if you have inserted some extra lines, if you imagine making this lattice more and more dense, where the number of sites is given by the total lattice here, the number of fermions stay fixed. So if you're interested in a box of 96 fermions, you make this lattice infinitely big. And with the appropriate scaling, that's a lattice discrete version of a continuum space. So you could model a continuum system this way by taking this limit. The number of sites over the number of electrons needs to go to infinity. And then if you want the thermodynamic limit, you have to take the number of electrons to infinity as well. And in order to do this continuum, you could replace the dispersion by better ones that control the range and so on. And for the Fermi gas, this U is negative, and it's uniquely specified given a scattering length, and this is thanks to work by Felix. So I'm going to use this now to give you a sense of how auxiliary field quantum Monte Carlo works. So this is a one-body term, obviously, it's a hopping, and there is a two-body term in red, which is an interaction. It turns out exponential of this two-body term can be written in that form, and this is referred to as a Hubbard-Stratanovich transformation. And this formula you can rigorously prove. It's very easy to prove because for each site, there are only 4 different cases. I highlighted here, double occupancy, 0, up or down. And you can just check the 4 cases that the 2 sides are equal. And this is due to Hirsch. But this formula is a mathematical identity, but it says something quite important. The two-body part on the left, so this is exponential of a two-body operator, is written as exponential of one-body operator, and then a sum. This is also now one-body, right? It's a field, x is a field, times one-body operators. Gamma is a constant that depends on tau, that's in front, and u. So x I will refer to as auxiliary fields. And so in words, what this formula tells you and what AFQMC, auxiliary field quantum Monte Carlo, executes is this principle that a many-body propagator or many-body system can be written as a linear combination, and your combination is x plus minus 1, of independent particle, and this is blue, so it's independent particle propagators, but they are under the influence of auxiliary fields. So this sentence is a mathematical identity, but it turns out numerically this is very helpful because a very hard and intractable problem with many-body physics can be turned into a large infinite number of independent fields. But it turns out with that you could do by Monte Carlo. That's the idea of AFQMC. So the idea is this. This is the one-body hopping, and this is the two-body interaction. I drew this as an abstract lattice. So this could be any problem. You write a basis. You define what C dagger and C are with respect to. And the two-body Hamiltonian has this form. And you can turn it into pictorially this still on the same lattice, but only this type of hopping, blue hopping, but they live in this fluctuating, my poor rendition of art, but the auxiliary fields are fluctuating, and you need to sum over them. Okay? So that's the idea of AFQMC. So now I'm going to move on and talk about AFQMC and how we think about the sign problem, or for those of you who haven't heard what the sign problem is, and then how to think about it. So the standard, a standard finite temperature method, Antoine mentioned this due to Black-Mackler, Scalapino, and Sugar from a long time ago. The many-body partition function, where beta is inverse temperature, has this form, trace of e to the minus beta, the Hamiltonian. And you can break this into little time slices, hence this tau that appeared on the previous page. So to compute some observable, you need this. And remember this little formula now I've compactified from the previous page, that e to the minus tau h can be written as sum over fields of this B. B is a one-body propagator, a mean field propagator. If you plug this in, I wrote this very explicitly, you have this form with all the x's for different time slices. Now, each of these B operators on a lattice of ns sites is a one-body Hamiltonian, the exponential of a one-body Hamiltonian, you can think about it as an n by n matrix. Right? The matrix elements depends on the fields, but it's an n by n matrix. So then, if you perform this trace over these non-interacting paths, what happens is it becomes a path integral over this entire set of paths and the determinant of 1 plus these products. So 1 is a matrix, n by n matrix. So matrix product, add diagonal 1, and then determinant is a number. And that will be the partition function. So, and then the idea is that you should be able to sample these x's by some Monte Carlo because it's a probability density function, and that's the original idea. The sign problem happens empirically. It appears that as you lower temperature or make this the number of slices more, lower temperature means beta grows, then this determinant seems, the average sign, this is sometimes negative, the average sign seems to go to 0 very quickly. And that was the empirical observation of what a sign problem is. But I think that's not super useful, and that's probably the exposure you've had to the sign problem. But we're going to now do a Gedanken experiment and try to understand what's happening. Apologies for this is probably the most technical part, bear with me. And also this is old, so apologies for the older form. You can see how old this thing is. The slide is old, right? So we have this partition function. I'm going to do a Gedanken experiment. I'm going to pretend that I know, whenever I need, I know what e to the minus tau h is. I knew the exact answer, but I'm going to pretend that I don't know for every time slice and carry out an experiment from one side to the other. So here's what I'm going to do. The P0 I know, it's a partition function, and it's positive. So now I'm going to imagine that I take the first one on the right and replace it by this little formula that we had before. Remember, x was in purple, the field. I'm going to replace one of these, the first one, by the sum, and I can swap the trace and the sum, so it looks like that. And this whole integrand is only over the first time slice of fields. I'm going to call this P1 x1. It's a function of the first slice of fields. And if we do this integral, we get back the first line. And now I go one more. I'm going to replace the second line by the same thing. So now this integrand is still integral. It's P2 and x1, x2. And so on and so forth until I've finished replacing all of these from right to left. Then I get back the same thing. And this integrand is called PL. And I'm using interchangeably integral versus sum. But it's the reason I keep calling it integral is because in the most general case, the Hubbard-Stratanovich transformation would lead to x's that are continuous. Although the formula I wrote to you, it's an Ising field. But the same idea applies. So we have the sequence. So what's happening if you analyze the behavior of these p's? You start from p0, which is the first line. That's positive. That's the whole partition function. Now if you replace this first slice, it's a function of x1. So what I'm plotting, this is as we go from right to left, we're doing this unrolling. We're changing one slice at a time. So now if I have a function of x1, then I can have, depending on what x1 I pick, different values of this p, this PL. So I've just plotted two, the green and the black, for the first time slice. And then I unroll more, and you should imagine this as a tree that's growing exponentially. It starts from the single point, and the branches come out more and more as we have more variables in this integrand. So I'm only drawing a couple of typical paths. But the only thing I'm interested in now is this, when this happened. Because it started here, where I can make tau arbitrarily small so it's continuous. So then, at some point, it would have to hit 0. If it doesn't, I don't care. The first time it hits 0 is this point, and I want to consider that point and ask, what does that mean? So if PL at some point is 0, it means all the future paths, in other words, I've finished replacing here, and if I were to continue and replace all of these with integrals and perform the integral, in other words, doing the sum of all these paths, I would get back exactly this current form. But this current form, since I cheated, I said I know the future answer. I already know all the future paths collectively would contribute 0 by definition. So in other words, whenever this path, this tree, the branch hits this axis of 0, then all the future branches, and there are infinite number of them, the entire family tree would add up miraculously exactly to 0. And then, for example, this green path, if it had to take a turn here, then there will be all more things. And anytime it touches 0, I've colored it red. Okay? And this green one is green because it never touched 0. And it started out being black, right? So anytime it touches 0, I color it green. If it finishes the whole thing, then it's, I color it red. If it finishes the whole thing, it's green. So a complete path would contribute to Z if and only if this stays completely green. So this explained to you the empirical observation that's often made why the average sign would go to 0. Because if you make this lower temperature means you're making this longer and longer. So if you carry out a random walk and you have a sink here, as you go longer, your probability of hitting the sink somewhere would be 1. Right? So whenever you hit, I've used some positive contribution, some negative contribution to indicate it's the kind of red path. They cancel exactly as we said before. Only the ones that can survive green would contribute. And of course, if you make this longer and longer, this function would be more and more antisymmetric. The green part would be vanishingly small compared to the red. That's why you have an exponential sign problem. So the sign problem happens whenever there's any path. You sample the stochastic field that hits a 0. It'll happen. The whole symmetry will take over. Now, symmetry can prevent this. So for example, if you have an attractive interaction and spin balanced, it turns out this never happens because the determinant we're talking about in here, up and down are equal, so you get determinant squared. Or if you have a repulsive half-fitting Hubbard model, then through particle-hole symmetry, the up and down become equal. So then there's a square. Then you can imagine this stays above that line and never touches the line. The probability at 0 is 0. So then there's no sign problem. And then there are more general formulations, for example, when you involve a spin-orbit coupling. I'll give you an example later. But that's the basic idea. It requires a special symmetry for this not to happen. In general, it happens. Okay, so once you understand this, there's a way to deal with the sign problem. You simply require, right, this is exact condition that you, as you go from right to left, you can require whenever it hits 0, you eliminate the path. It doesn't mean eliminate the negative. It means eliminate everybody starting from that point. Right? And then that would be exact. But of course, in the Gedanken experiment, we assume that wherever we are, we know what the projected future contribution is. We don't. So in practice, you use some sort of a trial density matrix that estimate the future contribution to eliminate the branch. And there are physical intuitions in terms of thinking why this is a good approximation, but this gives you a good limiting, it's based on a rigorous statement. But there are, I won't have time to go into the physical intuitions for why this will be good, but hopefully we'll do one of two things. We won't argue the formal part, but you're gonna see some results to give you a sense why this is a very good approximation. That's the approximation. Now I'm going to show you illustration of how this works. The order is slightly awkward. What this is a spin order in a cylinder. So this is like a Hubbard model at some fitting, repulsive Hubbard model. It turns out, later we'll see that, I think you all know that Antoine mentioned the antiferromagnetism in 3D. So in the two-dimensional version, it's also at half-fitting antiferromagnetic. One question we're very interested in, which I'll come to later, is when you dope it, what happens to that order? So here, imagine it's just a benchmark problem, that it has a finite width cylinder, and then this part, it's a cylinder, so it's a long cylinder lying down. This and this are disconnected open, but the top and the bottom are periodic. And we apply a spin pinning field up, down to induce a local antiferromagnetic order. And we ask what happens. So the reason we're doing this benchmark in this geometry is because a method known as DMRG, density matrix renormalization group, is very accurate for quasi-one-dimensional system like this. So we want to know what happens to the spin. So red is upspin, blue is downspin. And this is showing how the method works. This is AFQMC, but there's a self-consistent constraint. Basically, it does this constraint that I just told you about, but it backs out the BT from the calculation to feedback. Okay. So I'm showing a line cut along this horizontal axis, line cut of the spin density for a particular size. So this is with 4, which is in DMRG's is comfort zone. So what I'm plotting is the spin density along this line. It goes up, down, up, down, up, down, right? The edge has a pinning, so very big, and then it dies down. This is at high temperature, and you can see that you pin it at the edge, and then quickly the order disappears. It doesn't want to have antiferromagnetism. And this red symbol is without any control of the sign. And you can see it can, for beta of 5, it can sustain. But the error bar is very big. It's red one, and you cannot see an order. So now I'm going to use AFQMC to lower the temperature to 10, beta of 10. You can see this order picking up more. And lower it even more to 20, you can see the order picking up more. Now 30. Other than being antiferromagnetic, notice there's a phase slip. It goes up, down, and then 0, up, down again. So this phase flip turns out to be important later. This is the signature of a modulated antiferromagnetic state. So now I've put down beta of 50. This is effectively at the ground state now. And I've also put down the 0 temperature version of AFQMC here, and then DMRG, which is ground state. And you can barely see the difference. You can see some difference here, but you could barely see. So the ground state is accurate. It approaches the exact answer. And this is a paper we did with Antoine and former postdoc Beauchal. This shows that it's resilient. We use, on purpose, we're interested in the physics of U of 8. We use a Hartree-Fock U of 8, which is tremendously exaggerated. So in fact, in Hartree-Fock, the domains are AFM domains. So this is the staggered spin. So each color is one up, down domain. And then when the color changes, it means there's a phase slip. Right? So in fact, the Hartree-Fock solution we feed in is wrong because it does a stripe that's along the diagonal, one direction. And on a 4x4, it's just renditioned like that. But the actual answer is this. So we feed this in, and we start from this crazy domain-looking thing. And then by the time we're done, it finds an effective U, which is, it says, well, if you really want a mean field to approximate your solution, the right mean field U to use is 2.6 for U of 8, not 8. And it finds this answer, which, as I showed you on the previous page, is very accurate. So this is, in fact, we do the self-consistency with an effective beta. We're at a finite temperature as an actual physical beta, but the trial can have an effective beta and effective U, and you can see the system wanders through and finds an optimal path where the chi-squared is very low. So it goes from here, goes there. Okay, so that's sort of a flavor of how AFQMC works. I mentioned at the beginning that the advances in computational quantum physics came about because of algorithm development and because of collaboration and benchmark. So this is the earliest benchmark paper by the Simons collaboration on the many electron problem. This really played an important role. These are data from that paper, but it brought the greater community together. It reset standards and created dialogues for different methods to communicate. And these are additional papers of benchmark that were done, I think, on different systems that followed the collaboration. And then one key outcome is multi-method, multi-messenger synergy that not only are we comparing, but we group, we take methods together to complement each other and do physics, answer important problems. Antoine showed you this paper at half fitting at week U, how the different methods. So this plays both roles. This had some benchmark, but also brought very deep physical insight on the different crossover regimes, as Antoine illustrated to you. So that's sort of a flavor of methods. I am going to now move to the Fermi gas to give you an example where we could find synergy. So Tariq gave you a wonderful introduction. So the Fermi gas is these particles up, down, spin, live in a box. And the average interparticle spacing is d. You can figure out by volume and by number of particles. You have a Hamiltonian in first quantization that has the kinetic energy and then the interaction v. So the v, in reality, is more like this red curve, like a van der Waals, right? Atom-atom interaction. But because the range of v, in other words, this extent here, is so much smaller than d, you can approximate v by other shapes, like a well, as long as you reproduce the scattering length. That's the only knowledge that the system has. So then you can, once you have a square well, you can tune it. When it's deep, then particles are bounded, so you have molecules, B, C. And then when it's very, very shallow, you could lose a bound state. But in 2D, there'll always be a bound state. But it's weakly bound, so you have the BCS that pairs have very large size. They're not physically together, but rather in momentum space. And in between is the strongly interacting regime Tariq explained to you. And in 3D, it's interesting because 3D, the scattering length actually changes sign. In other words, it goes from not having a bound state to having a bound state, first bound state. You did this in your quantum mechanics homework, a 3D potential. In between, it goes through a place where there is the threshold for existence of a bound state, where the particle kind of, comes in, does kind of circle and then come out. That's where the scattering length diverges. And this is referred to as unitarity. At unitarity, because this goes to infinity, there's zero density, there's no other length scale. So then, since there's an attraction, the total energy of the system must be lower than the non-interacting problem, and yet there's no other energy scale. So EF is the non-interacting energy, and E is the interacting energy, so they must be related by a number, c. And this was recognized in the 90s by Birch, and it's called a Birch parameter. And this number, you would imagine, is less than 1 because the attractive interaction lowers the energy. But what is it? This came from this paper that summarized all the data that existed to predict the Birch parameter. It started from 97, which is when basically Birch posed the problem. And then there's different kinds of analytic results, experiment and simulations. And this is a summary. And this paper gave that last data point, this data point, the final one. We are very, so this is 2. That's an accidental synergy between computation and experiment. This is us, the green dot. And this is Martin-Zerlein's experiment here. And if you're standing where I am, you'll see that the green is to the left of it's a prediction. But the 2 came essentially at the same time. And it's a tremendous precision to do this. So this is a great example of how it can come together. Now, what I'm going to tell you about is 2D, where in 2 dimension, there's always a bound state. There's no unitarity. And the metric that Tariq showed you is basically the ratio of the scattering length to the interparticle spacing. Right, so log KFA. He showed you this as a function of x. So this is the equation of state we computed now 10 years ago. The red line as a function of energy minus the BCS energy is the equation of state. And there is a black curve, which is the previous 4 years earlier best result. And this is still probably the best known result because it's a QMC result. But it's actually not an exact QMC. It's a fixed node diffusion Monte Carlo. You can see that the 2 are not exactly together. So now what I've done is to plot our final energy in the thermodynamic limit as a horizontal line, and then plot finite particle numbers as a difference. And you can see that 10 particle, for example, is here, and eventually it converges. We went to 120 some particles. But DMC, you can see, is clearly, it's variational, so it's above. Right? And we were able to resolve this difference. And this is a later experiment that compared with our answer as well as the different limiting theories. So this is the condensate fraction as a function of the same log KFA. On the BEC side, there's about 80% condensate, and it goes to 0. And you can see the two limits, right? The BCS theory and Bogoliubov treating as purely bosons. The two limiting behaviors are correct, but in between, the interaction takes over. And you can look at the pairing wave function. So for example, here, it's a tightly paired wave function. So this is plotted in a 2D box, right? The wave function is very narrow. Two particles are closely together. And in the BCS limit, you can see the pairing wave function spans the whole wave function, and it's oscillating. In the middle, it has this feature. It has a peak, but it dips below and then goes back up. Right? The pair, this is reminiscent of what Tariq was showing about G2, I think. We also computed the BKT transition temperature, and that's this curve compared to various other calculations in theory. So Antoine was asking about BCS. BCS is this curve. On the right, it predicts the temperature quite well. And on the left here, we struggle to get to the very, very BC limit because we're doing a lattice. If the pair size is very small, we need to put a lot of lattice points between them. But that's the sort of strong interacting limit. And this is the final curve of the BKT transition temperature. And there's one experiment. You can see that on the BC side, it's agreeing quite well, but here it goes off. So to do this calculation required refining the standard AFQMC algorithm because you have to deal with a very large lattice to get to the continuum limit. So it turns out what it took is a low-rank decomposition to do this. We were able to improve the previous sort of best calculation with about 300 sites to 5,000 sites. And we could do a temperature as low as 0.02, order of magnitude lower than what was possible before, 0.2. And this is computing the gap. For example, I showed you this is at different places, but this particular gap spectral plot is for that point, and you can back out a gap. We have in this paper, we computed the gap across the BEC-BCS crossover. And the gap here in this region is sort of on the BCS side, but 2. The ratio of the gap to the transition temperature is 2.7. And this is surprisingly far from the BCS limit where there's a universal constant. I forgot, I think it's 1.7 or something. So it's not so BCS, even in the usual notion, we would think of this as quite BCS, but you can see that the temperature prediction is also off. Okay, I will just give you a laundry list of other things we have, just in case you're interested. We computed the contact, pairing correlations. You've seen that from Tariq's talk, momentum distribution, and the pair, the boson momentum distribution, and three-body correlations you saw from Tariq. We also computed dynamical quantities. One thing I didn't talk about, but I will mention here is it turns out you could add a Rashba spin orbit coupling, and this about 10 years ago experimentally there was progress in making a synthetic gauge. So there's lots of rich physics you could explore. So we did work dealing with spin orbit coupling. For example, looking at topology and spin-spin correlation functions. This induces triplet pairing, so this is the condensate fraction for triplet and singlet pairing and so on. There's detailed information, and these are exact calculations, so they're useful. And of course, you saw this from the beautiful talk, this potential synergy, and I think it's clear from Tariq's talk that there are many things one could do in these directions to gain new insight. So changing gears again, now talk about the Fermi-Hubbard model, repulsive interaction. The basic, you already saw in the benchmark how we were looking at spin-spin correlation. But the basic question to ask is, well, a basic question that's existed a long time is, to what extent does the simple Hubbard model contain cuprate physics? And this is a cuprate phase diagram I took from the internet. And so to what degree do we capture this with the Hubbard model? And I'll mostly focus on ground state and just a very, very narrow list of what some of the examples we've learned. This is a field that's been around for 40 years with many, many, many contributions, some in the audience. So obviously, this is not a summary. I'm just going to tell you a couple stories. So I mentioned, and you saw in Antoine's lecture, the 3D realization experimentally and the 2D measurement at finite temperature of the, at half fitting, zero doping on this phase diagram, that it's antiferromagnetic. The correlation is at zero temperature, long-ranged. So the question that's asked is, what happens with whole doping? And whereas on this side, whole doping means in this Hubbard model, we take some of the particles away. Electron doping means we add some particles in here. There's one up, one down on each side, and the capacity is 2, right? So you can add some particles. So that would be the electron doping case, and then what I'm indicating here is the whole doped case. Going back to this Birch parameter example, I want to use this to illustrate why this is computationally challenging. Imagine that you're not really interested in the Birch parameter, but you're interested in a qualitative question. Let's say, does the model superconduct or not? So let's say zero is, below 0 is not superconducting, above it is superconducting. And if you summarize all the data, you need to go back, because that's 97, right? Cuprates came about a decade earlier. And then this didn't stop like this calculation did. It continued. So basically another decade to the right, another decade to the left. And imagine whatever data points I have times 100. That's about the size of the literature. And you're going to have a distribution that kind of looks like this, right? And the disadvantage is there's not a huge amount of analytic results, and there's not been much in terms of experiment, right? So the challenge is that it's a delicate thing because the signal is very small. There are competing or intertwined orders that are separated by very tiny energy scales. For example, now we learned the signal for superconducting pairing correlations, if you create a D-wave pair and ask what is the pair-pair correlation function at large distance, if there is superconductivity, it's about 10 to the minus 4. So it's very easy to get the wrong answer. For example, here I'm showing you at half fitting where we know the exact calculations I showed you before in the Fermi gas. So this is as a function of 1 over L cubed. L is the lattice size. Going that way is to thermodynamic limit. And these are, each dot here is an exact calculation. You're interested in the thermodynamic limit. This is the energy per particle. So you do these calculations. And for example, that's a 4 by 4. That's the current record of exact diagonalization. You would be able to do this point. And then 6 by 6, 8 by 8, and so 10 by 10. And you extrapolate this, each of these points, unbiased. If you extrapolate it, you would get to that roughly where the arrow is. Now, it turns out the actual answer is what this blue-black line does. There's a tiny difference here. But that difference is the energy difference between a stripe order and no stripe order. So finite size effects is important. And the 10 by 10 is included in that extrapolation. Is very large, right? In general, it's hard to do. So if you do a cylinder, do a cluster, there are finite size effects. Or temperature, if you're coming down from high temperature, you need to get to low enough to get to the ground state. The ansatz, for example, recently there's a revival of variational calculations. You put down ansatz, one has to be careful that the ansatz doesn't exclude certain possibility or is expressive enough to capture different states. The approximations in the method, AFQMC, for example, is approximate, and is the approximation giving you the correct physics, or is it breaking down? The accuracy, meaning the size of the signal, and also statistical error bars if you have a Monte Carlo method, so on and so forth. So it's really not about getting the right answer per se, but it's the right answer for the right reason, and that's important. Well, the reason I'm saying that is that line, you have roughly 50% chance of getting the right answer if the answer is a yes, no, right? So this is ground state now trying to answer what happens in the ground state here. And this was an earlier paper with 4 methods trying to look at this doping, 1/8 doping, 125. And it showed that it's a stripe state. It's a stripe order. And more recently, we've mapped out the phase diagram, in other words, on this axis. And it turns out it looks very simple. It's stripe at high doping, at low doping, and then at some critical doping, for example, U of 8, which would be what cuprates is like, it turns into a now paramagnetic state. So basically it says, on this phase diagram, we're not seeing this green domain, but we're seeing a stripe phase, and then it vanishes. The stripes look like, this looks familiar from the benchmark we're looking at, so AFM, but with phase slips, with modulation. Okay? So blue, the red is upspin and blue is downspin. And the wavelength of this modulation is 1/doping. So the physics, how you understand going to the left to 0 doping is that the wavelength is 1/doping, so it's growing as you reduce doping, but when you hit half-fitting, it becomes infinity, 1/0, and that's how you recover antiferromagnetism. So we're going to call this a filled stripe. And the reason it's called a filled stripe is because if you imagine, so the reason we did this picture before, at half-fitting, it's antiferromagnetic, so there's no modulation. But when you take away some particles or you create some holes, the holes have to be put somewhere. The system figured out the way to put the holes is to have them cluster around a phase slip, right? So the holes have a higher density. Now, if you imagine the holes are completely living at the stripe, at the domain wall, then there'll be 1 hole per site on the domain wall. If you imagine it's just a line separating 2 domains. But in reality, we're going to see more clearly that that's far from the picture. The holes are actually quite mobile. But the name is inherited. It's called a filled stripe. Okay, a filled stripe means there's near the domain, or the period is 1/doping, or that on the, at the domain wall, there's 1 hole per site. So the temperature dependence we looked at, so the obviously question here. Actually, this is not, we did look at, but I wanted to highlight work done by Michel and Antoine. This is, I think, just showed up in Science. What they're looking at is finite temperature, and they're looking at the pseudogap boundary appropriately defined for different temperatures. And when you extrapolate the temperature, and that's finally this line going to 0 temperature, in other words, if you track the pseudogap regime and go down to ask what does that correspond to in 0 temperature, and this is with the diagrammatic Monte Carlo. And it turns out that line is in very good agreement with the ground state calculation from a different method. So this handshake between a finite temperature coming down and a ground state calculation obviously is very, very important and very reassuring. So we basically concluded, and this is just to follow up to show that indeed it is a striped state, absence of superconductivity in the pure. Pure means no T prime, and T prime is coming next. In this paper, we actually computed the pairing correlation and pairing order parameter. So in the Hubbard model, what I mean by pairing order parameter, this delta is you create a D-wave pair. In other words, you have upspin, you take the down, and you make this amplitude up, down, like a D-wave orbital. And you create a pair. You ask, what is the expectation value of that order parameter? Or you ask, if I have a pair like this and at some large separation, another pair like this, what is their correlation? And we do this by inducing, computing the order parameter by applying a finite inducing field and then extrapolating. So we scan the pair structure. D wave is the strongest by far. And you carry out the limits, I'll show you. And then there's no pairing. So this more recent work, we add T prime. So what happens is this. Now you have a, so Antoine showed you this Fermi surface, right? At half fitting, it looks like that, the diamond. And then when you dope it, it's these interior, these are equal energy, non-interacting Fermi surface. That's the Hubbard model. If you add a T prime, diagonal hopping, and that looks like this, then the non-interacting Fermi surface changes. This perfect nesting is broken. It caves in a little bit when T prime is negative. And now particle hole symmetry is broken. Particle hole symmetry separated by this perfect diamond. Now it's broken. Now you can ask both questions, right? You could choose a T prime and ask. So band structure calculations indicated that T prime is about -0.2, well, I mean, somewhere in there for YBCO, I think. So we took this value. There's a range, but we took this value and decided to look at the physics of T prime. It turns out we see great sensitivity. This is the pairing order parameter with a finite pinning field. And this is done on a cylinder. As I showed you before in the benchmark, Ly is the width of the thickness of the cylinder. So 1/4 means width 4. 1/6 means width 6. The reason there's only these two is because DMRG stops. It's fantastic at 4, and 6 challenges it, and going beyond as of now is difficult. So we're trying to do both benchmark and trying to explore something. So there are 2 points here, right? If you do periodic cylinder, which is the usual way of doing the calculation, and this is electron doped, you would conclude that there's a huge susceptibility for pairing, that the electron doped Hubbard model with this T prime is strongly superconducting. And in fact, there have been many papers that talked about this tendency. But if you connect the two by an anti-periodic boundary condition, in other words, a little flux through the tube, there's nothing wrong with doing that. It's a different boundary condition. Now, if you do this, it goes down like that. It would suggest that there's no pairing. Right? So this is a great deal of sensitivity. It turns out if you average over the different phases, you can close this. This is missing data points, but they're there. We extrapolate to much bigger size with AFQMC. The answer is here. So this is a synergistic study that lasted during COVID. This data now is all by AFQMC because now we do a supercell and we go to much wider systems, right? So the previous part, we first check the two methods and now we use AFQMC to go to large sizes. And this is the pinning field and this is the computed order parameter. And it goes from 20/4 all the way to 20/16 or something like that. And each of these data points contains the result of averaging over 12 random twists. We close the two sides. Now it's a torus, right? On the torus, we use random, quasi-random twists and do these calculations 12 times, average them. So each single calculation, if you figure that one, the bigger one, 20/16, the Hilbert space size is 10 to the 200, right? So really, this is not the usual, maybe a digression. One of the most trivial arguments you hear about quantum computers or why we can't solve any of these problems is that the Hilbert space is so big that it's impossible to solve the problem. Now, the actual thinking should be much more nuanced, right? I mean, when you don't have a problem, when you deal with a boson problem, you can solve a space that's much bigger. So any argument, for example, for quantum computing should be more profound, more sophisticated than that, right? Than just simple Hilbert space arguments. So then we extrapolate on each fixed pairing field, extrapolate to the thermodynamic limit. That's one of these lines. And then we plot the final thermodynamic limit answer and then extrapolate to 0 pinning field to get an order parameter. So when you do that, you end up with this pairing order parameter for hole doping and electron doping. And you can see that it, to a large degree, sort of is consistent with what we're seeing in the cuprates. The sensitivity we were seeing before reflects really intertwined and competing orders separated by small energy scales. You need the twist averaging boundary condition, and you need to be able to do very large supercells to high accuracy to detect this. It's a tiny thing. I said, so this order parameter is less than 0.02. If you square that, that's the pairing correlation you'll be getting. Right? The D-wave pairing order parameter resembles the cuprates. I already said that. So it turns out these superconducting correlations are in coexistence with stripes. So our intuition or our guess from the T prime equals 0 case was not quite correct, that we thought stripe and superconductivity competed and stripe won, so there's no superconductivity. Well, here with the T prime, there is superconductivity, but there's also stripes. And this is, for example, for this point, the optimal doping, I guess. You can see that this is the hole or charge density. The holes hint at the stripe at the phase slip, but the scale is from 0.1 to 0.15. So it's a tiny fluctuation. The holes are cluster a little bit near the phase slip. And this period is not 1 over doping anymore. It's a fraction, which is less than 1. And if you go to C, the overdoped regime, you can see that basically the whole density is a constant. But there's still a stripe, and it's still a fraction. And we spent a lot of effort trying to do very large systems to figure out what this fraction is. You can see as you go to the right, it's trying to go to the thermodynamic limit. But we were never able to converge it. But one thing we see very clearly is that it's not an integer. It's not 1 or 1/2, which is what current predictions have been based on, mostly DMRG, right? But that's because it's very narrow cylinders and periodic boundary conditions. So it's a fraction that's between somewhere 80% to 75%, something like that. And on the electron-doped side, we see nail antiferromagnetism, which is also sort of consistent with the cuprate phase diagram, although we seem to be seeing a coexistence, which is a little inconsistent with the experiment. I am running out of time. So this you saw from Antoine's... Thank you. You saw from Antoine's lecture, latest result from Marcus Greiner's group, where the temperature is comfortably now below 0.1. And we know that this is their half-fitting at a U of about 8, what they measure, the spin-spin correlation function. And this is a line cut, and it's staggered. So it's -1 alternating. So that's why if it's plus minus, it's going to now all be positive. And a long-range correlation would be a constant here. But this is at different temperatures. It's our result, our calculation. So for example, at 0.25 would be this red curve, which is where experiments were stuck at for a long time, about 0.25. And then this is 0.15 and 0.1, and ground state is this top one. You can see the data falls between about 0.1 and 0.0. And so the actual, so this is serving as thermometry, but the actual temperature is now below 0.1. And then this is half-fitting, the left. The right is doped cases with different doping, but short-range correlations, where we've done the calculation, which are these lines for different temperature. And then these are different, so 1, 0, 2, 0, something, 1, 1, the different, well, it's indicated here, sorry. 1, 0, and 1, 1, and 2, 0, and so on. And you can see that it's also, the temperature is consistent with being lower than the lowest temperature we compute, or sometimes even lower than our ground state, but I think that's small systematics in the experiment. So this is very exciting because now there's an opportunity to really look at the more challenging physics in the Hubbard model. Another slight change of gear. This is a collaboration with Martin Zulein's group looking for FFLO. So basically, this is a negative U Hubbard model. Martin has been studying, for example, his measurement of single-on, double-on correlation. So the setting is now that you imagine there's a magnetic field that polarizes the system, although in experiment it's not a magnetic field, it can just be polarized. So we have a negative U Hubbard model, which if it's not polarized would be more like the case that Tariq talked about. It's a sign problem-free exact calculation we could do. But now with polarization, it has a sign problem, so it's AFQMC. And here's experimentally measured single-arm, double-arm correlation, and the bottom two panels are theory, and you can see there's quite good agreement. And we look at the indicator for an FFLO order, this is the sign of the pairing correlation function. So if the sign changes, it means so the pairing correlation function should be a constant if it's long-range ordered. But if there's indication for FFLO, it would be positive, and then sometimes it's modulated, so it'll turn negative. And you can see that, so this is short-range correlation at high temperature, and then it changes shape, the order parameter, and then changes shape again. But eventually it starts to have one domain and then a negative domain and then a positive again. It starts to change sign. But this temperature, of course, experiment is not quite here yet. So what we did is, in this paper, careful comparison at about 0.25 of every quantity they measure, and then we use AFQMC to go down to below this temperature to look at. And it turns out the earlier indications are the same kind of physics that eventually at low temperature lead to FFLO. So I think this is very exciting. There's opportunity to really experimentally probe. Let me thank my collaborators. The Hubbard model, Fermi Hubbard model, was done by a former student, Hao Xu, with help from former postdocs. Mingpu Chen was with me, and Jiaming was a postdoc with Ule and Steve. So this is a Hubbard collaboration. And then Chunhang, I showed the calculation she was doing with Marcus and Martin, and Bo Xiao, Yuan Yao, and Antoine on these finite temperature studies, and Hao and Ettore on a couple of the gaps, and also this Hubbard model calculation, and of course Tariq, you already met, and Marcus' group. So yeah, this is back to the outline to remind you what we did. I hope I echoed the excitement that you got from Antoine's lecture about the opportunities for both computation and experiment, really hand in hand with precision comparisons. I talked about the 2D Fermi gas and the Hubbard model. I showed this to remind me to say that I talked about AFQMC with the Hubbard-like interaction for Hubbard-Stratanovich. It turns out for any interaction, you could do a decomposition. So the method you could then do for example, molecules. So there's a branch where we do quantum chemistry with transition metals and so on, with essentially the same technology, but with some beefed up numerics. Thank you very much.